Welcome back, and this is lecture 37. So we were discussing power amplifiers, so let's continue in that vein. So we discussed various topologies like class A, class B, class C power amplifiers, their efficiencies, the metrics of importance, and so on. Among the things that came out was the fact that the one of the metrics that is other than the fact that we need to deliver large power, the efficiency of a power amplifier became drastically important, right? So it's an important metric to optimize for, and the extension to that is the fact that we had talked about this briefly, but let me formalize it now. So if you have a PA, which is basically a voltage control current source, and it has an output resistance R0, and it has to deliver a power to some load RL, then what do you want R0 to be, right? So to maximize efficiency, eta, we want RL to be much less than R0. But RL is not in your control, but R0 is in your control, because this is the stuff that you are designing for, right? This is in your control. So which essentially means that we have to design for R0 to be much less than RL. Now note that, i.e., not for matching, right? So this should be, obvious, because if you recall that analogy of if you are designing this and you want to maximize the power delivery to RL when you have control over RS, you would want RS to be equal to 0, not equal to RL, right? So it's analogous, this is not an equivalent, it's analogous to saying that R0 has to be much lesser than RL, right? So you design PA to maximize efficiency for these purposes, and this should be evident by now, because we were seeing that how we would like to down convert RL to a smaller value and so on, right? We would like to have all the output swing to go on to RL, right? So this is number one that we needed to get out of the way. Another important thing that we need to get out of the way is the fact that I have been talking about power gain, right? We have been talking about this is a power amplifier, which means the gain of the power amplifier is equal to P out over P in. Now, if you have a common source topology, you might be tempted to think that the power in is 0, because input doesn't have any resistance. It's a capacitor. The capacitor does not dissipate any power, and so on, right? So this power amplifier gain should always be infinity, which is true at very low frequencies. But recall now that your transistor has a gate, which is a capacitor, and if you recall again, the gate is not a single point, right? So gate has a routing, so you'll have a resistance in the gate, and also this capacitor is distributed, and which means that the signal flows in through the capacitor and goes to the source or the drain, which has a resistance also, right? So which essentially means that the effective model, a very simplistic but not so bad model, is to say that you have a resistance Rg, which includes the physical resistance of the gate polyrouting and the some part of the channel resistance, and you have a CGS capacitor, okay? And obviously you have I out, which goes into the load and creates all the gain, right? And you have a source here. You have a source which has Rs and goes in, right? Now, if things are inside the chip, then probably Rs can be very high, right? You do not have the long routing. So let's assume that there is a source. We are not particularly concerned about from where this is coming, and let's not even bother with the fact that we have to match that interface, right? If it's inside the chip, if this is inside the chip, if inside the chip, then matching not necessary. Right? So this is true only for RF frequencies, not millimeter wave frequencies, by the way. So that you should keep in mind. Okay, fine. So if that is the case, then we have to find out what is the power that is going in, right? So note that when I say power that is going in, I am talking about this box. So what is P in? Because RG is a part of the system now, right? So let's see. By the way, what are we interested in? We are interested in finding out the voltage across VGS, because I out is GM times the VGS, correct? So let's assume the current that is going in is I in. Okay, so if the current that goes in is I in, so I in is how much in terms of VGS? So I in is basically j omega, if I just write the amplitude part of it, so I in is basically j omega CGS times VGS, right? So VGS is the voltage across the CGS capacitor, right? So the impedance of the admittance of the capacitor is j omega CGS. So the current through the capacitor is j omega CGS times VGS, which is effectively equal to I in also, right? So the amplitude of this I in is omega times CGS times VGS, which means that the power in is half I in square times RG, which is half omega square CGS squared VGS squared, right? VGS squared times RG, correct? Okay. So what is I out then? I out, I know, is GM times VGS, correct? And where does the I out flow out? The I out effectively flow out to RL, correct? And we assume that RL is much lesser than R out. But let's forget about that assumption. Let's for the timing, let's assume that this entire I out flows into the R out, right? So if I out flows only into R out, then your P out is basically GM squared VGS squared half times R out, correct? Now what is VGS squared? I can get VGS squared from this equation, that is half GM squared R out times VGS squared from that equation, which is twice P in by omega squared CGS squared times RG, right? Okay, which means P in over P out, or P out over P in, is how much? This cancels. I know that GM over CGS is omega t, so this becomes omega t by omega whole squared times R out over RG, right? Which means your power gain is omega t by omega whole squared times R out over RG. Now, just like in case of a voltage gain, we had this transit frequency omega t, right? So we would like to be interested in finding out what is the maximum frequency beyond which you will not get any power gain, correct? So if I set this to be equal to unity, then that frequency where I get a power gain of at least a power gain of more than 1, I call this omega max, which becomes omega t times under root R out over RG, correct? So clearly, I mean, we can do some sanity check. Firstly, if we assume that RG is 0, then omega max is infinite, right? Which means that any frequency I go, I should be able to get power gain, which makes sense. Because why does it make sense? Because if RG is 0, then there is no power that is going into the common source amplifier, right? There is no power dissipation, but I am getting power output, right? Because the transistor is drawing power from the voltage source and all, right? So I'm getting power output, which means that your power gain is infinite always. But because of the presence of RG, right? Because of the presence of RG, you are going to get a power gain only till a finite frequency. Okay, and what is the intuition behind that? Because of this RG CGS capacitance, right? Firstly, you are not going to get any voltage. The voltage that you are going to that is going to drop across the CGS is going to decrease as you keep on increasing frequency. But more importantly, as the frequency increases, the CGS is drawing more current, right? Which means the more current, more power is getting dissipated across RG naturally, right? So you are, in order to get more output power, you are also not only taking power from the source that anyway you will have to take. Now you are also taking power from the input, whatever is driving your PA also, right? So sometimes you might feel that we know so many ways of resonating out this CGS and all, right? We can resonate out this effect, but the effect of RG will never be able to resonate out, right? So the effect of RG will remain. And remember that when you resonate out all these things, I mean, if you do the series to parallel conversion of this RG and CGS, for example, then what are you going to get? You are ultimately going to get that RG will be multiplied by some Q squared and all, right, which comes in parallel, and that is not an actual resistance, right? So the value of the RG will also that effective resistance will also be dependent on the frequency, and hence the impact of the frequency dependence will still persist. Okay, fine. Firstly, sanity check. If you assume RG to be equal to 0, then there is no meaning of omega max, because omega max will go to infinity. Now at very low frequencies, right, where CGS is, I mean, omega times CGS is very small, then fine. I mean, you can make that assumption, but I mean, if you are anyway working at much lower frequency, you shouldn't bother about omega max, right? So this is important. These omega values of omega max, just like omega t, is important when you want to push the frequency at higher and higher values, right? So that is number one sanity check. Number two important consideration is the fact that your R out is generally much more than RG, right? So RG will be of the order of few ohms, and R out, even if you are trying to drive like hundreds of milliwatts of power, I mean, you can have R out of the order of 50 ohm, 100 ohm, and so on, right? So effectively, omega max can be like 3, 4, 5x of omega t, depending upon how you size your transistors, right? So that's a good thing, right? It looks like I can get power gain till higher frequency than voltage gain. That's a good thing. Another thing that you have to watch out for is that this expression that we got was under the assumption that entire I out flows into R out. Now, if entire I out flows into R out, I mean, nothing flows into the load, right? So you effectively do not really get any power gain. If you have to get power gain, and if I have to honor the fact that if RL is much less than R out, then your omega max becomes omega t times RL by RG. Now, what is RL? RL is basically, if you are trying to drive high power, this RL is effectively the effective load impedance, right? So that 50 ohm antenna load, you are transforming down to value of what, 10 ohms or so, right? Maybe 10 ohm, 5 ohm, depending upon how much output power you want, with the maximums, while ensuring you have maximum swing, you essentially try to reduce the value of RL, right, seen by the common source amplifier. So if you want to reduce that value of RL, then clearly this under root this RL over RG goes towards unity, and your omega max also reduces, right? So you see that if you want to drive higher, larger and larger power, there seems to be a trade-off between how much power you can deliver to versus what frequency you can deliver it at, given that you have a constant on the voltage supply. And the last point, so let me also write down these points, right? So the first point was at low frequencies, don't worry about omega max, right? And number two is IP out RL is much less than 50 ohm, or I should say much, instead of less, I should less than 50 ohm, i.e. RL by RG tends to 1, right? This RL by RG tends to 1 might be an exaggeration, maybe 2, maybe 3, maybe 4, or whatever, but omega max tends to omega t, or if you lose omega max, right? So which means that trade-off between high power and high omega max. Correct? Next thing is not apparent from this expression. The one that you should worry about is the fact that for high power, right, for to prevent breakdown of devices, generally when we talk about breakdown, we are talking about breakdown of the transistor junctions, right? We need thick oxide devices, right? So which now thick oxide devices, or rather I should say large TOX devices generally have non-minimum L rather, right? So which means their their omega t is less than omega t max of thin TOX device, right? Which means that, but the good thing is that for a thick oxide device, higher power supply. So this is a bad thing. This is a bad thing. But the good thing is can use higher. Typically, I mean, if I have to take typical examples in CMOS devices, let's say you are using a 65 nanometer technology, the minimum channel length for a low voltage transistor will be about 60 nanometer, but the maximum VDD that you can use for a low voltage transistor will be about 1 volt, 1.1 volt or so on. If you go to a higher thick oxide device, that maximum 1 volt can go up to 2 volt, 2.5 volt and so on, but the minimum length goes up from 60 nanometer to more than 200 to 50 nanometer, right? So you can see that the omega t will reduce naturally because you are scaling over by 1 over L squared. You can now afford to get higher swing, right? So there is also a trade-off between the frequency at which you get, I mean indirectly this is a trade-off between the power that you can deliver versus the frequency at which you can deliver the power, right? Okay. So these are important trade-offs to consider. The other thing that you should be aware of is the fact that this is something we have not talked about in detail, but we should be aware of it nonetheless, is the fact that in a PA, when you have all these contraptions, right, you have large swing here, right? You have a matching network and all those things I can understand. This is all good. But effectively you have large swing here. So what does it do? Now the large swing here, I mean under the assumption that things are not breaking is not a problem, but you should consider the fact that there is a CGD capacitance here. And note that there is not only large swing, there is a large transmission line, right? On top of that, we have not implemented matching, right? Okay, so there can be a really large swing and that swing can come here and there can be routings here and so on, right? So what I'm trying to get at is that at high frequencies, at RF, a PA is not an unilateral device, right? I.e., if you go back to your Y parameter model of a two-port network, if you go to your Y parameter, so you have Y11, Y22, Y12, Y21, correct? So this kind of gives you the input impedance, this kind of gives you the output impedance very roughly. This gives you the gain, but this gives you the feedback, right? So this is the feedback term. So in a unilateral device, this feedback term is 0. And that's why you can unconditionally make a unilateral device stable. But if you have a non-zero feedback term, that is Y12 is not equal to 0, which means there is a feedback from output to input, and if there is a phase lag and delay and so on, right, at some frequency of interest, then there can be instability, right? So you have to take care of look out for basically this is y12 is not equal to 0 or s12 is not equal to 0, right? So potentially unstable if not taken care, right? So you can do analog circuit equivalent of measuring the phase margin and all, run your AC simulation and find out the location of the poles and find out if there is a peaking and all those things, so on and so forth. Or you can do S parameter analysis to find these out. We do not have enough time in this course to get into the details of the stability. I'll see if I can give you the expressions that one needs to look out for, but what you need to understand is the fact that at these frequencies PA is not a unilateral device. Now this was not particularly a problem in an LNA. If you recall, one of the reasons it was not a problem because we could put a cascode device, correct? So here also in principle we can put a cascode device to reduce that feedback from output to input, but the problem is that cascode device is going to eat up headroom, and moment the cascode device eats up headroom, you lose the amount of current that you are flowing through the entire device plus the headroom multiplied by the headroom will be the extra power loss. Already you are struggling with getting 50% efficiency in a PA, and on top of that if you use a cascode transistor to get stability, then that becomes even more of a problem, right? So that's why in most PAs, high power PAs, you do not have a cascode transistor. Okay, these are some of the things that we should be looking out for. Okay, so another issue with PAs is the fact that when you talk about efficiency in a PA, that 50% or 78% whatever efficiency we calculated was under the assumption that you have maximum possible swing all the time, right? But in principle you do not have maximum possible swing all the time because the signal amplitude also varies, right? So if you recall the expressions of efficiencies, then it will be evident that if the swing reduces, if the output swing reduces, the output power obviously reduces, right? But then the power that is consumed, that is PDC, never changes, which means that as you keep on reducing the output power, your efficiency goes for a toss, right? So one important metric to characterize PA is power efficiency at back off. Now what is back off? Back off means that let's say you have a P1 dB number for your PA, and obviously at P1 dB you have 1 dB compression of the signal. That's the definition of P1 dB. But maybe you have designed your PA in such a way that P1 dB is 20 dBm. But that essentially means that when you are expecting a maximum input amplitude, so the output amplitude is also maximum. Hence, at those frequencies, as those settings of the input out amplitude or the output amplitude, you are going to get so much of efficiency at P1 dB. But in other times when the input is not that high of an amplitude, the output will also reduce in amplitude, right? So which means that your power, even though the power consumed by the PA does not change, the power delivered changes, right? So which means that the efficiency reduces, correct? So efficiency of a PA at a back off power, that is back off as in how many, maybe 1 dB below the maximum power, or maybe 2 dB below the maximum power, or 3 dB below the maximum power, is a metric of importance. So naturally you see that there is an issue with the amount your efficiency at back off drops. So which means that you need to have ways to ensure that if your input amplitude varies, your efficiency does not drop as much. And the way people have come up with ingenious ways, right, so to figure out how to about doing it. So if this is your PA and let's say this is your input, the issue is the input is not of fixed amplitude. The input can be something like this, then suddenly it increases, then it reduces, and so on. So maybe your PA has maximum efficiency around this time, is this around when the input is swinging peak to peak, when the input is within these smaller bands, your efficiency is pretty low. So what people have figured out is that, so this envelope of signal swing, this is a pretty low frequency envelope. Right? So if we can detect the envelope, right, and then essentially change the power supply itself, right? So you detect envelope, and then modulate VDD essentially, correct? So you essentially have an envelope detector, and then once you detect the envelope, you have a LDO or a low dropout regulator, or I will simply say the regulator, which powers the PA, correct? Which powers the supply of the PA. So this the VDD of the PA will also go like this. So this is the VDD of the PA, which means that when the input is at low amplitude, the VDD will also come down so as to ensure that you are not unnecessarily burning large amount of power. This is one way of increasing efficiency. Now, easier said than done, but you should be able to appreciate the fact that this, whatever extra circuitry that you are putting, this is not supposed to work at RF. This is supposed to work at modulation frequency, right? Okay, so this is one way of increasing efficiency. Another very important issue with the PA obviously is the linearity. Because naturally, because you are talking about signals of high amplitude, which means linearity is a problem. By the way, noise is not necessarily a big problem in many cases of the PA. You have to take care of it. Your PA cannot be too noisy, but simply because your PA guzzles so much of power, right? The noise versus power trade-off helps is in our favor. That is, when you're burning so much of power, naturally the signal to noise ratio improves. So generally, you do not have to, for high power PAs, you do not have to bother about thermal noise as such, right, for the standalone PA. But linearity definitely is an issue. Now, out of band linearity is taken care by the filtering, but what about the in band linearity? So then obviously you have to use multiple techniques. If you recall, we talked about some of the high frequency linearization techniques in LNAs, for example, the feed forward technique and so on, which are not based on feedback, which are also used in PS to linearize the PS. I am going to briefly talk about one particular technique which is particular to a PA, and it is a feedback based linearization, which is something that you cannot use in the LNA side, right? So now when we say feedback based linearization, you might wonder that, hey, the PA is operating at multi-gigahertz frequency, how can you have negative feedback? If you have negative feedback, the loop bandwidth also has to be much higher than the frequency of interest in order to get a certain amount of loop gain, which means it becomes a problem, right? So that is why what people generally do is we appreciate the fact that we ultimately want to linearize the entire transmitter chain, not necessarily the PA, right? So what do we have in the PA? So if you think carefully, we have a DAC, right? Then we have a mixer. IQ and all I am not showing you. We know that this is what it is. Then maybe you have a preamplifier, and then you have a PA, right? This is your load, and maybe you have a matching network. I'm calling it a filter, and you have a load, right? The thing that we should note is that this part of the circuitry is working at low frequency FBB, right? And this part of the circuitry is working at RF, right? So if at all I have to use feedback efficiently, I have to use the feedback at the low frequency part of the circuit, not at the high frequency part of the circuit, right? But ultimately we are looking at the output. So maybe I can take the output, right, mix it down again with FLO, use a low pass filter, right? So now when I do this, what do I get? I get basically the baseband signal back, right? It's almost like a receiver, but for a known signal, I'm getting the baseband signal back. Now, if I have distortion here, right? If this point is distorted, this distortion is going to travel all the way here, which means that now I am in the baseband domain, and in the baseband domain I can use, so these are the digital bits that are coming in, correct? So what I can do is I'm showing here, but you can do it in digital also. I can put an ADC, and then this come out, and I do summation and error correction, right? So I do a DSP here, I correct the errors, right? So this is a error correction block, and feed it to the DAC, feed it a pre-distorted output to the DAC, right? So and we keep doing this till my observation point is this is the observation point. So we keep doing this till the observation point is we observe perfectly linear baseband input, right? So because we know what we are trying to send, if we are receiving whatever we are trying to send with low amount of distortion, then we know that whatever we are transmitting is also good. But the key thing to note is that this is easier said than done. This path has to be perfectly linear, has to be. Now perfect linearity is a myth, you will not be able to get. The only thing is that it has to be much more linear than the forward path. I mean that whenever you have a feedback based thing, obviously your sensing path has to be almost close to ideal. So in this case it has to be much more linear than the forward path. Other thing is that you have to ensure is that this is not only about the amplitude, you also have to match the amount of delay, right? Because the signal has a certain amount of delay as it goes from here to there. When the signal comes out, it also has a certain amount of delay. But what are you comparing with? So you have to ensure that the round trip delay, right? If the delay from the input of the DAC to the PA is very long, right? Then you are going to, which essentially means that from the output of the PA to the output of the ADC, again you are going to have a very long delay. Then you will not be able to compare the right bits. Correct? So when you are comparing the bits, which means that you have to ensure that the delays are also appropriate. Not only that, this FLO, these two FLOs, right? Even though they are supposed to be working at exactly the same frequency, they need not necessarily be at the same phase, right? Because again of the delay thing, right? So the signal that goes from here to here has some delay, signal that comes from here to here has some delay. There will be transmission line, and so there has to be a phase alignment in certain ways, right? There has to be a certain amount of phase delay. So this is easier said than done. In a block diagrammatic representation, this is possible, but I mean this type of loops, which are by the way often regularly used, are extremely useful in ensuring that your inter-transmitter chain is linear. This type of loops are called digital predistortion loops. This or DPD, linearization technique. Okay, fine. There are several other ways of linearizing. I mean, at least I wanted to give you a flavor of what are the ways people think about linearizing. So now, till now, what did we talk about the PA? We talked about the important metrics. We talked about what matters, what doesn't matter. Mostly power delivery, efficiency, and linearity, right? We talked about whether matching is required or not, and so on and so forth. And the most important thing always is it boils down to the efficiency. Now it seems that from whatever we have talked about, it seems that when you have to deal with PS, if you have a class A amplifier, you have 50% efficiency, or definitely less than that. If you have class B, 78% efficiency, and so on. But the question is, can we think of radically of something different so that I do not have to deal with this class A, class B, class C amplifiers at all? The reason I'm asking is that why are you talking about this back off? Why are you talking about the amplitude of the signal and so on, right? So if you think about it, in a sinusoid, there are three things that we need to bother about. Actually, there are two things we need to bother about. One is the amplitude, other is the phase, right? Till now we have not really talked about phase at all. We have only talked about amplitude, and we have basically assumed all the time that the entire information is embedded in the amplitude, right? So now if we talk about types of modulation, what is the amplitude modulation that we have mostly talked about? We have talked about basically it's amplitude modulation or AM. But how do you make AM? It's a all digital world, right? Inside the chip, it's a digital world. So effectively, we do ASK, which is amplitude shift keying. And basically, the crudest version of this is the fact that if you have, let's say, you want to transmit a bits of 1, 0, 1, 0, and so on, then what do you do in a very block diagrammatic sense? You have, let's say, sine A, sine omega or omega LOT. From here you send the bits which are 1, 0, 1, 0 and so on. At the output, what do you get? You get something like this, and then 0, then something like this, 0 and so on, right? Now this is why I showed for like 1 bit. If you want to modulate it like with 2 bits or multi-bit, then this will have different amplitudes. Need not necessarily be 1, 0. You can have combinations of 1, 0, 0, 1, 1, 1, 0, 0 and so on, right? So this is while sending 1 bit. We could have sent like multi-bits at a time. We could have sent 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0 and so on. And then so like this. So in that case, my output would have looked like this high amplitude, that is 1, 1, then maybe slightly lower amplitude, that is 1, 0, maybe slightly lower amplitude is 0, 1, then flat, then something like, then again maybe 0, 1 and so on, right? So you kind of see that there is a modulation, there is an envelope that is getting developed. So this envelope you feed it to the PA, correct? Now the thing is, you do not directly feed it as is. You also push this through some sort of filter, because otherwise you kind of get abrupt endings of a symbol, right? So abrupt ending means that you develop high frequency components. So you do not directly feed it. You put another set of filtering, smoothening filter, and then you send it off. Okay. So now the thing is, we also know that we need not necessarily always send information in terms of amplitude. Right? We can send information in phases, right? So before going there, let me talk about how sometimes these type of symbols are often represented. See, these are often represented in terms of a constellation diagram. So let's say I am only sending 1 and 0, single bits we are sending, correct? So what we generally tend to do is to say that either if let's say I call this the 0 point, then I say if I am sending only 1, I'll mark off a point which is somewhere here, and we call this 1, and this is a point which is calling 0. Okay, so which means that at certain point of time, and this 1 and 0 are representing the amplitude of the signal that I am sending, correct? I am sending, let's say, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. So in that case, maybe I will have 4 of these points marked off. I'll maybe have 0, 0, 0, 1, 1, 0, 1, 1. And if I am nitpicky about this and I say that the maximum amplitude is always constant, I cannot really go across the amplitude, then maybe I have to say that if I am sending 1 bit, then this should be 1, right? Within this band, I have to, if I am trying to send multiple symbols, I have to accommodate the multiple symbols within that band, right? So let's say this corresponds to VDD, then the value corresponding to each of these symbols have to be shortened, right? Okay, fine. But this is all we are saying, that we are modulating the amplitude. But as I said, we need not be limited to modulating the amplitude. We can also, as we know, we can send 90-degree modulated signals, right? I and Q. which means that I can also say that maybe I call this the I-axis and maybe I call this the Q-axis, and I say that I can send a signal which is I can basically multiply with a cosinusoid and I can multiply with a sinusoid. Correct? Maybe I'm multiplying with a sinusoid. I am then talking about this axis. When I am multiplying with a cosinusoid, I am talking about this axis. Correct? So, okay. So which means that I should be able to now put constellation at these points at along these axes as well, right? So which means that I can have one point here, one I can put here, and maybe this is the one I'm calling it 0, or maybe I call it -1. Doesn't matter. This is a construct that we are coming up with, so as long as we are consistent, should not be a problem. Similarly, on the Q side, I can say this, I can say this, and so on, right? Correct. So now, if you think about it, so before I go there, let me take a step back and say that instead of sending here 1 0, I could have sent 1 -1, then +1, then -1. Then what would have happened? I would have gotten a sinusoid like this. Then it would have flipped, right? It would have gone like this, then again flipped, it would have gone like this, again flipped, and so on. Correct? So this is, I am sending 1 here, which means that till here I am sending 1, then I am sending -1, then I am sending 1, and so on. Correct? But the note that good thing about this is the amplitude of whatever I am sending is not changing. Right? So now think of a PA in which I am sending this kind of modulation where the amplitude does not change. Then I can always operate the PA at its maximum efficiency point. I don't have to work at back off. Correct? So which essentially means that if let's say now I have a cosinusoid and a sinusoid where I can now send, let's say, I mean, again, this is 1 -1, which means that I can now send 4 symbols. Earlier I was able to send 2 symbols, now I am able to say 4 symbols, 2 in each of these channels, and combination of these, which means that I should be able to send a constant amplitude signal through only modulating the phase, right? So if you think about it, this I can say is essentially modulating the phase, right? Because I am multiplying with my +1, I am multiplying with -1, I am going from 0 to 180, 0 to 180, so on, right? So here I can say that I am going from 0 to 90 to 180 to 270 and then back to 0, right? So I am having phase rotation, so I am doing four types of, able to send 4 symbols without changing phase at all. Correct? Similarly, I can also say do a combination of I and Q, right? I can add up these constellation points and ensure that everything, I can get intermediate phases, just like I could have got an intermediate amplitude, I can get intermediate phases, and I can have this constellation point somewhere in between also, and which means that so these type of modulations are often called quadrature phase shift keying, or QPSK, right? So PSK means only you are going from 1 to minus, you are changing the phase between you are changing the phase between 0 and 180, 0 and 180, and so on. Here you are basically changing from 0 to 45 to 90 and so on, right? So this is so essentially you are using the entire you are using multiple points on a constant amplitude circle, right? So also these are called constant amplitude modulation. Similarly, since we are doing at this topic, you can do a combination of these, right? So since we are in the topic of constellation diagrams, let me also point out a couple of different types of constellation diagrams that are often used. For example, if you do not choose to use QPSK and you want to have different types of amplitude and phase simultaneously, right? So then you can choose a constellation diagram which is something similar, something like this. For example, you can have right? So this is called 16 QAM, right? It's called quadrature amplitude modulation. The term should be self-explanatory, because you have amplitude modulation, because you see that you have two types of, you have different types of amplitude. You have one amplitude here, you have another amplitude here, right? Similarly, you also have different amplitude here. You have different types of amplitude. On top of that, you have quadrature modulation also, right? Because these are, you have 45-degree and you have 90-degree, and at 45-degree, 90-degree phases and all, right? So each of, depending upon which constellation diagram that you are, or which constellation point that you are targeting, you will have a specific amplitude and modulation, right? So this is called QAM, quadrature amplitude modulation. If you have 64 QAM, for example, and if I concentrate only on one quadrant, in one quadrant of a 16 QAM, you have 4 constellation points. If you have 64 QAM, then you are going to have, in, let's say, 64 QAM, you'll have in one quadrant, we will have 16 constellation points. The amount of margin that you have from in going from one constellation point to another, the distance between them will keep on decreasing if you increase the number of symbols that you are sending, correct? Which essentially means that your signal to noise ratio requirements in your transmitter will be higher if you are using a denser constellation with respect to another constellation diagram which has smaller and smaller, or rather I should say which has less dense of a constellation point, right? So that is something also you should keep in mind, right? So there is a trade-off moment you try to squeeze it, pack in more and more symbols within the finite amount of power supply that we have, right? You are changing the phase between 0 and 180, 0 and 180 and so on. Here you are basically changing from 0 to 45 to 90 and so on, right? So essentially you are using using multiple points on a constant amplitude circle, right? So also these are called constant amplitude modulation. Similarly, since we are doing at this topic, so if we are using a constant amplitude modulation and we go back to our PA, then which essentially means that the input of the PA is always happening a constant amplitude. The phase might change. The phase might change from time to time, but the input of the PA has constant amplitude, which means and note that that there is no information in amplitude at all, right? So in constant amplitude modulations, there is no information in amplitude, which means that I can as well forget about linearity issues because of amplitude issues, correct? All the information is there in the phase, all info present in phase. And what do I mean by that? So now consider you have a square wave which is operating at TLO or FLO. So let's say this is TLO. When I am modulating it with a let's say a low frequency sinusoid, right? So what should the amplitude modulation or should the phase modulation look like? Now where is the phase information? The phase information is in the zero crossing, right? So how do I know phase? In a square wave, where is the phase information? The phase information is basically I know that in a square wave, between when I go from one rising edge to another rising edge, I cover 2 pi, correct? So let's assume the second rising edge moves by theta degree from 2 pi, then that theta is essentially the information. right? So that theta, the amount of time your zero crossings differed by, which means the phase with which your zero crossings deviate from its ideal value, right, is essentially the baseband, is the amplitude of the baseband signal, so as to say, right? Which means that if I do modulation here, how should it look at, how should I go about thinking about what the square wave will look like? It will probably look like, let's assume the first edge doesn't move, and around the second edge you have a peak of the baseband. Let's say this is baseband, this is RF. I have the peak of the baseband signal, which means that the edge will move, the rising edge will move by a large amount, right? So which means that the rising edge, which was rising edge of the RF signal, which was supposed to move here, will move maybe somewhere here, right? So then again here I have, looks like I have some heavy amplitude but slightly lower than whatever we had. So instead of moving here, it will move here, and so on, right? So the deviation of the edges from this ideal, I mean from its pristine point, is essentially the information of phase, correct? But the key thing to note is that this is all constant amplitude. Now if I feed this guy directly here, right, all I will be interested to find out the zero crossing of the current that is coming out, right? So if it is an ideal amplifier, or rather it will, I mean, let's assume this goes from 0 to VDD, then this common source amplifier does not really work as an amplifier, it becomes a switch, right? And it switches at the zero crossings, right? It switches somewhere else at certain instances when it crosses threshold voltage. But as long as these information of zero crossings are retained in the current, I am able to transfer the signal information from the input of the PA to the output of the PA. But note that all I am interested is the zero crossing information. I am not interested in the amplitude, which means that I can operate this PA as a switch, because switch preserves that zero crossing information, correct? So which means that I can operate this guy as a switch, where I have constant modulated signal, let's say a PSK signal, right, constant amplitude signal that comes in, and this, I have this inductor here, and I have this matching network, and it goes to the antenna. Now, so this can be, again, this can be I mean your NMOS transistor, but now the NMOS transistor acts as a switch. And again you have this matching network, and you have a antenna. But obviously what problem do you see? The problem obviously is the fact that when you have, these are not sinusoidal currents anymore, these are like very hard switching current, right? Either the transistor is off or on, which means that you need filters, because otherwise you are going to have a lot of harmonics at the output, which means that the matching network plus filter becomes critical, correct? And these type of power amplifiers are often called switching power amplifiers. These are called switching. And since they only operate as, these transistors only operate as switches, you do not really have to bother about efficiency, right? In principle, there is no power consumption across the switches, as long as you ensure that, I mean, the current and the voltages are not overlapping during its switching period. There is no power dissipation in principle. Theoretically, there is absolutely no power that is dissipated at the switches, right? All the current can flow into the load, which means that in principle, these type of switching amplifiers can give you 100% efficiency, right? But obviously you cannot, because obviously there will be some amount of overlap of currents and voltages. There will be some dissipation of power, but you can get pretty good, much better power efficiency than the class A, class B, class C kind of PAs. Or they, by the way, they are now, we will refer to them as linear power amplifiers, because they operate in the under the assumption that the output current is proportional to the input voltage, and then you do all sorts of filtering. In this case, we're calling them switching power amplifiers, right? So switching power amplifiers have better efficiency, but so this is good, but the bad thing is it has switching harmonics, which needs to be filtered out. So almost always when you use switching, I mean, if linearity is a very big concern, out of band emission is a lot of concern. People generally don't tend to use class D, switching power amplifiers. By the way, I mean, these type of amplifiers also have multiple topologies, and they are named after ABCs are over. They are called D, E, F, and so on. And all of them, I mean, these different topologies are based on how do you shape the currents and the voltages so that there is no overlap between the currents and the voltages when the transistor switches, so that the power dissipation across the transistors is kept minimum. But again, the key thing is that all these switching power amplifiers have very good efficiency, right? But if you are limited by the amount of passives that you can use for filtering, then you have to deal with lot of out of band harmonics, and hence in many cases where out of band emissions and harmonics are of importance, switching power amplifiers are not used. But having said that, there are many IoT based applications where switching power amplifiers are used, because the emission masks, or rather the out of band emissions that you will have to deal with, regulatory aspect of it will be much lower, right? I think, I mean, that's all we have to talk about PA. I will stop here and we'll see you in the next class.